There we go. So, if you're just joined us from the recorded version, apologies, didn't start recording from the beginning. I'm on question 3 of the direct hydration. Without people here to prompt me, it's easy to forget certain things. So we've just looked at this first bullet point. So what we've got then is we've got the conditions for the hydration reaction, and now I need 2 advantages and 2 disadvantages of the fermentation method compared to the direct hydration method. Again, I'm going to follow this in question order, so I'm going to go for the advantages first. Fermentation would happen at room temperature generally. We talked about it in question 1, around about 30 degrees would be acceptable. So as an advantage, I've got easier conditions for the environment and indeed energy costs. So a lower temperature would be perhaps a good way to answer that question. You can make reference to pressure because you would use an increased pressure for hydration, but I'd focus on temperature because I've already stated that hydration is going to be 100 degrees and therefore I'm going to be working at a lower temperature. You can see in brackets there I've made reference to the energy use. As a chemist, I think I prefer to focus on the chemical aspect of it, so the detail of how the reaction proceeds, rather than just a vague answer that says it uses lower energy. I'd like to qualify that with showing that I know the conditions. Now, another advantage is, of course, it uses a renewable resource, glucose, and is obtained by plants, and therefore it's renewable, whereas the ethene for direct hydration would often be obtained from crude oil, and therefore could be described as a non-renewable resource. So again, focused in there on my 2 advantages, I'm almost at the end of the question. And you can see so far, I've said 4 things, and I'm picking up a mark for each. 2 marks at the beginning for the 2 conditions for hydration, another 2 marks for my advantages of fermentation, and I've now got to specify just these 2 disadvantages. That's what's going to come up next, and therefore I'm going to get my final 2 marks. Now, with these disadvantages, I've got a few that I could choose from, and I've picked as the top 2 the ones that I think are the most chemically relevant, because fermentation is a lot slower as a reaction compared to hydration. Hydration at a high temperature and often a high pressure is going to be a fast reaction, and I can get my ethanol quickly. And this question, of course, is focused on the synthesis of ethanol. In this particular case, fermentation would give me a slower production rate, and that isn't necessarily a good thing. Another option, and I think it's perhaps an obvious one to think about when you consider the equations, which are not written down here, but I will make reference to, is that the disadvantage is that it's got a lower atom economy. Hydration of ethene is an addition reaction. The atom economy would be 100%. There are no waste products. It's ethene and steam reacting together to make ethanol. With fermentation, I'm going to produce carbon dioxide. And carbon dioxide is going to be a waste product. And so actually, that would lower my atom economy. Now, for me, they are the top 2 disadvantages, and they were the 2 that I would give in an exam. There's another one that's got a chemical consideration, and it's worth mentioning, and that is when I do this fermentation process, the product I get is not pure. Yes, it's part of that aqueous solution mixture. There's the spent yeast would be part of that mixture as well, and I'm going to have to purify that product. Now, if I think back to hydration, it's an addition reaction that only makes the one product. That product, ethanol, would be pure. I wouldn't need any further purification steps. And so there are actually 3 things I can pick from here using my chemical knowledge. I only need to give 2, and if you were answering this question, I would advise you only give 2. But I'm showing you the 3 possibilities here because you may have picked different ones from me. Now, question 4, again, you can kind of see when you scan down through the words, there's another reference to fermentation, but it's not quite a standard fermentation question. When we read from the top, it says that British scientists have used bacteria to ferment glucose and produce the biofuel butan-1-ol. Now, of course, what we've got to do here is a long list of things. I'm going to work through the first of the list to show you how it works, and then show the answers from the other part. So let's just focus for the time being on this first bit here. Write an equation for the fermentation of glucose, and I'm given the formula C6H12O6 to form butan-1-ol, carbon dioxide, and water only. Now, this isn't a reaction I know. This is one where I'm going to have to apply my knowledge and to kind of problem solve a little bit. So I'm going to follow what the question says. I'm going to take glucose and I'm going to ferment it. Fermentation is a natural process. There are no other reactions. The yeast, and it would be a catalyst in this case, we're saying with bacteria rather than yeast, and we're getting a different product. Now, one of the products is butanol, and one of the things I would advise here is if I'm asked to give a particular organic compound as a product, I would make sure that the examiner could see clearly what my structure was. And so butanol is a 4-carbon alcohol, and I'm going to show each of those carbons individually. The OH group is on carbon number 1. I'm going to show it at the end of my chain. So I can see here I've got carbon 1 with the OH group, carbon 2, carbon 3, and the final carbon is a CH3. To say my advice here, if you're asked to give a specific organic product, I would show the structure of that product rather than work with a molecular formula. It can communicate to the examiners that you understand the chemistry that's happening. Now, my other products, I'm told I've got carbon dioxide and I'm going to make water. So I'm just taking these out of the question. Focused on the butanol. There you go. I've put my carbon dioxide in, and I've also got here my water. So they are the products. I now need to have a look and see if my equation is balanced. I start with 6 carbons. I've got 4 in the butanol, and I've got 1 in the carbon dioxide. To me, that's automatically a suggestion that I should perhaps be thinking of having 2 moles of carbon dioxide produced. That would show where my 6 carbons ended up. I need to take into account hydrogen as well. 12 in the glucose. Well, if you count them through the butanol, there would be 10. There are 2 in the water, so actually that's going to give me my 12 hydrogens. So hydrogen is looking balanced. And in fact, that has solved it, because when I consider the oxygens, there are 6 in glucose. I've got 1 in the butanol. I've got 1 in the water. And when I take into account both carbon dioxides, that gives me a further 4 oxygens, and I have 6 oxygens on each side. So that reaction that I've never met before, I've been able to follow the question, bring in the products it suggests, and then once I've drawn that, just check it's balanced to get my first mark. Now I'm going to change the screen here because that answer will come up in a moment, but you can see what I've done, like I did with the previous question where I was asked quite a lot of things. I've just given myself some sort of reference points, some bullet points. So I've done the first one, I've shown you that equation, you'll see it again in a moment. So I've got my second statement there. I need to state 1 condition necessary to ensure complete combustion of a fuel in air, and I need to write an equation for the complete combustion of butanol. Actually, this bullet point's a little bit sneaky. It's asking me to do 2 things, and you can see here, if I underline what it's asking me to do, I need to give that complete combustion equation, but I also need to state why butanol can be described as a biofuel. And so, of course, you can see with the 4-mark question, perhaps 1 mark for each bullet point, and the second bullet point there, the final one, giving me requiring 2 things. Now, I've taught you through that top equation already, so let's scroll down. Complete combustion requires excess oxygen. I need to ensure that my supply of oxygen is sufficient to mean all of the carbon atoms end up as carbon dioxide, and that I don't form either solid carbon or carbon monoxide. So excess oxygen is perhaps the best description for that process. It shows that I've got plenty of oxygen, I would get complete combustion. My combustion equation then for butanol is quite tricky. Now, I've drawn it up as an answer, but if you're following with your own work here, just kind of pause and just check your balancing. Because butanol, we said there were 10 hydrogens, and those 10 hydrogens are going to end up in water. And I would encourage you perhaps to balance these combustion equations, focusing on the water first and working backwards. Because I've got 4 carbons, and therefore I would get 4 carbon dioxides. And now I know my balancing numbers for my products, I could start thinking about the oxygen atoms. And what a lot of people will do here is look at the 4 carbon dioxides, and they would simply say, okay, that's going to be 4 moles of oxygen. I've got 5 waters there, so that's 5 oxygen atoms, 2.5 moles of oxygen, and we'll think to write 6.5 O2. And one of the tricky things about balancing equations of combustions of alcohols is you need to make sure you consider the oxygen that is already part of that alcohol structure. I have one of those 6 of one of those oxygen atoms already in my reactants, and therefore I would only need 6 moles of O2 in my final balanced equation, not 6.5. So if you're marking your own work and you put 6.5, I would suggest it's probably because you've not considered the oxygen in the alcohol, and that would be a common mistake that examiners will see frequently in exams. So that's 3 of the options done. I need to state now why this butan-1-ol can be considered a biofuel, and I wouldn't normally consider that, except in this case, and I've scrolled back to the top of the question, I'm told that I'm obtaining it from glucose. I can ferment glucose to produce butan-1-ol, and in this context, it is a biofuel. So, what would my answer be? Well, I'd learn my definitions. I'd go back to my alcohols 1 notes, and I would see that a biofuel is something that's obtained from a renewable biological source. And in fact, that is the key word. I've underlined it there. In this particular context, the butan-1-ol is being obtained from a biological source. It's being obtained from glucose from plants, and therefore can be considered as a biofuel. Now remember, if you do have comments, I can see kind of a few things coming up in the windows. Ruth is on hand. She's looking at those at the moment if you're following live rather than the video, and she will get to your comments as she can. A couple more questions in this first pack, and so we'll have a look at this one, which is question 5, and I'm going to work through question 5 for you here because there's some more advice then that we can give you. So you've got a big table, and again, this has come from a bigger question, and we've just got a small snippet in the pack that you're working with. So not a lot of these alcohols, not all of these isomers are going to crop up. But the one that does is isomer 4. And it tells you at the beginning of the question that 2 different alcohols can be obtained by the hydration of isomer 4. So I'm just going to highlight isomer 4 here at the top of the screen. That is the chemical that we're dealing with. And we can make 2 alcohols. Now, when I read the question, what I'm expected to do is I'm expected to use this displayed formula, and we've seen that once already. But also, not only that, I've got to draw a product. And I have to draw a product that is oxidized readily by acidified potassium dichromate. So that is oxidized readily by acidified potassium dichromate. Now, I think the way to tackle this is to recognise that we are therefore going to produce an alcohol that's primary or secondary. They would be readily oxidised and not tertiary. Now, I'm going to do the first thing is I'm going to work with isomer 4 here. So I'm going to draw out as part of my working isomer 4, but I'm going to do it as a displayed formula because then I can adapt it for you to show you what the product would be. Now, of course, with isomer 4, I can see the name. I've got butene as my structure. That tells me that the carbons in the double bond are carbons 2 and 3. And when I look at that structural formula, the beginning, where I've got this CH3 twice, is sometimes awkward to draw. So in this case, I'm going to start from the other end, carbon number 4, and work backwards. So carbon number 4 is part of a methyl group. And I track back to carbon number 3. And for the moment, I'm going to show carbon number 3 as being part of a double bond. At the moment, I'm drawing isomer 4 before I answer the question. Then I get back to carbon number 2, and of course, carbon number 2 is bonded to these 2 methyl groups, but I am asked to draw a displayed formula, so I'm going to show every atom and every bond. So now I've got isomer 4 on the screen. I just need to understand what this hydration reaction would do. Well, the hydration reaction would react this alkene with steam, with water. And what's going to happen is the double bond is going to break open, and so it's going to become a single bond, and each of these atoms in the double bond is going to be bonded to something from water. Now, of course, when the water reacts in this process, it breaks into 2 distinct parts. It breaks into an OH group and a hydrogen. So the options I've got, of course, is to put these groups in certain places. And that's what I would do, is I would just consider where they would go. Now I could put, move the right thing. I could put the OH group in this position just here. Now that would work, that's a possible product, but when I look back at my question, this isn't going to be the right answer. This particular alcohol would not be oxidized readily by acidified potassium dichromate. It's a tertiary alcohol. The carbon bonded to the OH group is itself bonded to 3 other carbons. Highlight them there in pink for you all, but briefly, so that's not going to be the right answer. So let's get rid of the highlights. Going back a bit too far there. What I'm going to do is take that OH group and put it in a different position. Now the position it would have to go in will be on the next carbon in the chain. That is going to therefore give me a structure now that is a secondary alcohol because the carbon bonded to the OH group bonded to 2 other carbons, crucially still has a hydrogen attached to it, so it could be oxidized. Now at this moment I know what my product is, and as I was saying at the beginning, and for apologies again if you're following the video, I didn't start it at the beginning of the questions, this still wouldn't get the mark because it's that classic error again. I've shown the OH group, but I haven't shown it with a displayed formula. A displayed formula would show the atom and the bond, and that's what I would be expected to give as the correct answer for this product. Now the final question in this Alcohols 1 review is looking at ethanol. And again, you can see when I've just scanned down the question, I've bullet pointed the key things that I'm being asked. There's some information in the question that's perhaps important to consider as well. So ethanol is an important fuel, and I'm told here I can make a dilute solution of ethanol by fermentation. Now I've highlighted that and I'll come back to that particular statement as part of the answer. And of course you can see here that at the end of this sentence, or this little section, I'm told that it's suggested that this therefore could be classed as a carbon neutral biofuel. What am I expected to do with this particular question? Well, I've got these key statements that I'm being asked. Can I write an equation for the fermentation of glucose to give ethanol? Can I state 2 of these essential conditions that would give me a good yield? And then can I name a process to produce more concentrated ethanol from this reaction? And you can see there's a 4th bullet point just creeping at the bottom. We'll go for the yellow. Can I state the meaning of the term carbon neutral in the context of this biofuel? And as I've done before, I'm going to go through each of these in the order they appear in the equation. In the question. The equation for producing ethanol should be in your memory banks. It's one that you should just learn. C6H12O6 is going to give me 2 moles of ethanol and 2 moles of carbon dioxide. That would be my balanced equation. Now I need to give 2 essential conditions. Now we saw at the beginning in question 1 that I was asked to give 3. So there are 3 things I could say here, but I'm only going to get marks for the first 2. So I would say the 2 that I'm most confident with, and I've got them in the same order as I had them before, yeast, because I need that as for the enzymes, anaerobic, I do not want oxygen there because that would actually oxidize the alcohol, so I don't want oxygen present, and a sensible temperature, which as I said, the mark schemes tend to like something around 25 to 40, but it's an enzyme process, and biologists will know that 35, 37 degrees is a good temperature for biological processes. Now that's given me 3 of my 5 marks already, and that's the first 2 bullet points covered. The trickiest actually when you look at this question is the 3rd one. Name a process to produce more concentrated ethanol from a dilute aqueous solution. Well, if you think about that, to turn my ethanol into a more concentrated solution, I need to remove, if you like, either the water from that solution or the ethanol from the water. And the easiest way I can do that is to remove the ethanol from the water. Ethanol has a lower boiling point from the water. How do I separate 2 liquids? Well, the technique to separate 2 liquids would be distillation. And in fact, if you look in your notes for this process, we would say that fractional distillation is required, and that would be the technique that you would be expected to give. If you take the ethanol out of that solution, you should get a purer and therefore also more concentrated sample of ethanol from your reaction mixture. Now, the final part is this reference to carbon neutral. Carbon neutral, you've got to be careful with your words here. Examiners will kind of pick up on precise phrases. That's what they'd be looking for. And so you can see here that we're going to say there is no overall emission of CO2, but we're going to say the context, and that's in the production, but also the use of the fuel. So in the production of the fuel and the use of the fuel, CO2 will be involved. However, when I consider both processes together, the amount of CO2 used and the amount of CO2 released is about the same, and therefore it's considered carbon neutral. Now that concludes the comments on this first alcohols pack. I'm going to just close it down, open the second one. If you're following it in the video, there'll be obviously a slight pause while I change this around, same for the people at home as well. So you now got on your screens the first question from Alcohols Review 2. And you can see I've put the answer into the first one already, and we will talk about this as we go through it. Propane 1,2-diol has the structure, and you're given your structural formula, and it's used to make polyesters, and it gives you some more information. Now, of course, we're talking about an oxidation reaction. You can see here a sample of propane 1,2-diol was refluxed with a large excess of potassium dichromate 6 and sulfuric acid. So the first thing you're asked to do is draw that starter material, the skeletal formula. A skeletal formula would show carbons just as changing the directions, and the only atoms you should see would be the atoms like oxygen and halogens, and hydrogens should only be shown if they're bonded to something that isn't carbon. Now in this case, of course, I've got my 3-carbon chain, so I've got what is carbon 1, carbon 2 and carbon 3, and that's my skeletal formula of the carbon chain. And I've got my OH groups there on carbons 1 and 2 because I'm told it's a 1,2-diol. Now one of the things that you need to bear in mind if you're drawing these structures is just make sure your links are accurate. When you draw these, the bond should be between the carbon and the oxygen, and you can see in my diagram there that's exactly what's happened. Examiners refer to it as connectivity. Have you connected the atoms together in the right order? And the carbon should be bonded to the oxygen, and then you can put the hydrogen next to the oxygen. Now we've got that as a starting point, it's something that we can use to refer to, because the next question is actually quite a tricky question. I write an equation for the oxidation reaction of propane 1,2-diol under reflux, and we use O to represent the oxidizing agent. Now, of course, what I've got here is I've got 2 different alcohol groups. I've got this first one here on carbon number 1, which is a primary alcohol. I've got this second one on carbon number 2, which is a secondary alcohol, and both are going to get oxidized. Now, in the context of this reaction, then, I'm using reflux conditions, and you can see here I've made a little note to myself. The primary alcohol here is going to get oxidized all the way to a carboxylic acid. That oxidation step itself would require 2 moles of oxidizing agent. I would expect, if I look back in my notes, that that's what I would see. 2 moles of oxidizing agent needed to turn a primary alcohol into a carboxylic acid. The secondary alcohol is going to require 1 mole of oxidizing agent to go into a ketone. So I'm bearing that in mind when I begin to think about this balanced equation. Now, when I show you the answer, I'll comment on all of the parts as we go through it. You'll see what I've done. I've got my starter material and I've drawn it out. And you can see straight away that in terms of my oxidizing agent, I've already made reference to the fact that I need 3. 2 to convert the primary alcohol to a carboxylic acid, 1 for the conversion of the secondary alcohol to the ketone. And you can see in my product that's what I've done. I'm going to talk about the product in a moment. Now, when you oxidize an alcohol functional group, you always form water. And in this case, we're going to form 2 moles of water. And we're going to form 2 moles of water because I've oxidized a secondary alcohol, but I've also oxidized a second alcohol group, the primary alcohol. And in oxidizing 2 groups, I would expect 2 moles of water. Now that equation is balanced, and the balance in numbers and the correct product would get you 1 mark. But again, you can see, and I've got reference to it in terms of the text I've put up here, the displayed formula is required. We mentioned in the previous section that examiners love to ask displayed formula for things with OH groups because students are it's just too tempting to just write OH rather than showing O and then bond H. So just look at your structure if you've answered this question. Make sure there that your OH group is shown as displayed, showing the O and the H atoms, but crucially the bond as well. That is the way you would get the 2 marks for this question. Now, of course, we now start thinking about practical considerations. You were told that this oxidation happened under reflux, and in happening under reflux, you're expected to be able to draw the apparatus. There are no marks for artistic skill in chemistry, which is good, but what you are supposed to be able to do is kind of give a schematic diagram that would seem appropriate for the experiment you're doing. Now, when you're asked for a labeled diagram, really you should be thinking about labeling the equipment. If you look in the notes, we've drawn these diagrams for you, and actually you've got lots of labels there. We've been telling you about chemicals that you would use and other things that you would have present, but a labeled diagram should focus solely on the equipment in the first instance. So you can see at the bottom there we've got our flask, and it should be either a round bottom flask or a pear-shaped flask, and it should have a condenser. And again, I've got the condenser labelled here, and the condenser is vertically up, and that's the way it should be arranged, so that any vapours that would come out of my reaction vessel could condense and go back down in, and that's what reflux is, continuous evaporation and condensation. For good measure, I've put in the water. Water should go in at the bottom and out at the top, and I would encourage you to do that. Examiners would want you to know how to set this piece of apparatus up, and so showing which way the water flow is demonstrates you have that knowledge. And so 2 marks here, generally 1 for the flask being labelled, 1 for the condenser being the right way around, but sometimes these questions are quite picky, and if you draw the wrong type of diagram, you'll end up with just 0. You do need to focus on the equipment that you would need. Now, to finish off with this part of the question, we're considering some of the other products. Oh, before we do that, we've got anti-bumping granules. So why are anti-bumping granules placed in the flask? But anti-bumping granules prevent bumping, and so you're not allowed to say they're there to prevent bumping. That's already mentioned in the question. Bumping is where you get large bubbles that just kind of automatically kind of flow up into the condenser and cause issues. What an anti-bumping granule will do is allow small bubbles to form. And I like this as an answer. I prefer to make a positive statement. Anti-bumping granules allow small bubbles, and that is going to prevent larger bubbles from forming, and those larger bubbles are what chemists refer to as bumping. So, final part of this question is a consideration of a different organic product when the acidified potassium dichromate is not in excess. So that means that those alcohol groups are not going to react fully. Now let's just remind ourselves what this alcohol was. So just draw it back up in this corner over here. We were thinking about the oxidation of propane 1,2-diol. And propane 1,2-diol has these 2 OH groups. In the context of an excess of dichromate, I would expect the first of these groups, the secondary group, to form a ketone, and the primary group there on the left, on the right, to form a carboxylic acid. If I don't have an excess, then I'm going to get mixtures of products. And I'm only suggesting 1 as part of the question, but I will show you all of the options that you could come up with. So you can see here you're going to get a mark for any one of these structures, and I'll talk through each structure in turn. So the first one I've got here, put a little blue border around it. You can see there that I've oxidized what is the secondary alcohol to a ketone, but I've left the primary alcohol unreacted. That is a possibility. Now, of course, I could leave the secondary alcohol, and we'll go for our second blue box. The secondary alcohol here is unreacted, and the primary alcohol has been turned into an aldehyde. That is another scenario. And in this corner, well, at this end here, again, another blue box going around it. Again, the same idea. I've left my secondary alcohol unreacted, but this time formed the carboxylic acid at the other end. Or my final option is that both of those OH groups react, and we'll do this one in the red pen, it's there in the centre, but this time round the ketone is formed, but I've only got partial oxidation of the primary alcohol. It hasn't got enough oxidizing agent to turn it into a carboxylic acid. It doesn't matter which of these four structures you give, but you need to give one of them to get the mark. These would all be possible products, and you're just asked to draw one. Just draw a different organic product. So it's just the one that you're expected to find, and any one of those would do. Now, question 2 in this Alcohols Review 2 booklet focuses now on some physical properties. We've got some data in a table, and of course, we've got the question. Now, I'll go straight for the question here. Explain, with reference to intermolecular forces, why distillation allows propanol to be separated from the other organic products. The other organic products, of course, are in the context of oxidation of this alcohol, where propan-1-ol could form propanoic acid. And in fact, I would expect a reaction mixture containing these three compounds, and distillation is good for maybe removing the propanol. So I'm going to refer to the intermolecular forces. That's what the question wants me to do, and so you have to use your words carefully when you answer this question. Now, the question is about propanol. Why can propanol be separated? So I'm going to start my answer by focusing on propanol. The intermolecular forces between propanol molecules are permanent dipole-dipole attractions. So I've identified the intermolecular force. The carbon double bond oxygen is a polar group. You'll have seen it in the aldehydes and ketones topic, and so I would expect permanent dipoles to form in that molecule and therefore get permanent dipole-dipole attractions. Now, I need to think about the other two compounds then, but fortunately one statement will work. Propanoic acid, well, the carboxylic acid group is COOH. Our alcohol propanol has an OH group, and as an A-level chemist, you would be expected to recognise that compounds with an OH group, molecules containing an OH group, will form hydrogen bonds. And that's what my second mark is going to be for, recognising that both propan-1-ol and propanoic acid would have hydrogen bonds as the intermolecular force between their molecules. Now, with 2 out of 3 marks here, I need to now comment on why propanol can be separated. Now I've identified my intermolecular forces, I need to make reference to their relative strength. It's quite a long sentence I've written here, but we're kind of focused on the key part that the examiners would be looking for, and it's simply this. The intermolecular forces, so these permanent dipole-dipole forces in propanol, are weaker. That means they're going to be easier to break. I've given a full answer, I like full answer here, so they're weaker than the hydrogen bonds in the other examples. How does that allow it to be separated? Well, you can see I finished my sentence here. It will evaporate before the other molecules evaporate, and so that's why it will come off first and be separated. But your key marks here are for identifying the intermolecular forces and commenting on the relative strength of those forces. Now, we're staying in the context of this reaction for what happens over the page. It's just a short question. Describe how you would carry out a simple test tube test to confirm that my propanol obtained by distillation didn't contain any propanoic acid. It's a funny test to do because we're confirming that something is not there rather than something is there. And actually, it's easier to kind of give the positive observations, and that's what I've done in my answer. Propanol, I'm expecting to be there. How do I know that I haven't got any propanoic acid? Well, I'm going to test for that carboxylic acid. And so coming back out of your knowledge of acid reactions, you can see the reagent I would pick here would be sodium carbonate. You could use sodium hydrogen carbonate. You could use, in fact, any carbonate, magnesium carbonate, but it tends to be straightforward to focus on the ones that you've met commonly, and I suspect most of you would have written sodium carbonate. Now, sodium carbonate would produce carbon dioxide when it reacts with an acid. So you can see here I've given the observation to show what would happen if propanoic acid was there. That's fine. That's allowed to be done. What I'm saying is that I take my sample out of that I've obtained by my distillation. I would take a small sample of it, add some sodium carbonate. If I saw some fizzing, I would know that the acid was there. but actually if I didn't, then of course that propanol would be free of carboxylic acid. So they would be your 2 marks there. And it looks like a simple question for 2 marks. And there's another one of these where the examiners give you loads and loads of lines to write things, and you don't always need to fill the spaces. But one thing I will say is that you will get a swing in questions like this between 2 marks and 0 marks. Because if you don't know the reagent there that I've highlighted in yellow, or you write the wrong chemical, you will automatically get 0 for that answer. So it is worth knowing your chemical tests. Because, as I say, 2 marks should be easily obtainable if you know the correct reactants. Now, the final 2 questions in this pack are focus on reactions, and this first one is a bit tricky. So we're going to go through this one, and I'll do it live for you as I talk about it. You can see we're talking about dehydration of alcohols. We've got our concentrated phosphoric acid, but we're going via a carbocation intermediate, and we're going to form an alkene. Now, the question starts here really with what I'm asked to do. I've read the background information at the top of the page. I need to complete the mechanism for the conversion of 2-methyl cyclohexanol into 1-methyl cyclohexene via carbocation D by drawing, and I've got to put in the structure of the missing intermediate and the necessary curly arrows. Now, one of the things that you'll see when you're given mechanisms to complete is you should be given the information that you need. And the first step in this acid catalyzed dehydration is that the acid plays a role. And in fact, you should be drawing a curly arrow from the lone pair of the OH group to the H+ ion that has come from the acid. So that first picture has given you everything you need, and you then should draw the intermediate obtained from that process. Now we'll go through the marks as we do each step. So that's my first mark. There's 4 available here, and I've got my first mark for that curly arrow. The intermediate, I'm going to focus first of all on the bits that haven't changed. The cyclic ring is still the same. I'm going to use the same sort of format that the examiners have given me to draw the rest of the molecule. And I'm going to focus on the bit that's changed. We'll draw it here in the blue pen. Because that OH group is now OH2, it's picked up a second hydrogen, but not only that, it should be positively charged, and we do the charge there in red. So I'm on to my second mark now. I've got 1 mark for my first curly arrow, and I've got 1 mark for being able to draw that structure. But when I look down underneath it, I can see that that structure is going to form this carbocation, carbocation D. Now, of course, I need to show a curly arrow for that formation, and you can see that the OH2 group, or water, has come off that structure. I need to show a curly arrow. Curly arrows need to be shown accurately, and you'll see in the notes that we suggest you start either from a bond or a lone pair. I would always aim to start in the middle of a bond, and I would always draw my curly arrow to the atom that it goes to, and in this case, that curly arrow would go to the oxygen. That would form water. And so I'm going to get a second mark in this little section for that accurate curly arrow. So I'm on 3 out of 4. The final mark will come for completing the conversion of carbocation D into my desired product. And of course, what you can see in the desired product, if you start looking at some of the changes, is that in carbocation D, we've got a hydrogen here that I'll highlight in purple, and that's gone. We'll get rid of the highlight, and we'll look at another difference. And in my final product, there it is, I've got a double bond, and I can see that that double bond is between the carbon bond in the CH3 group, and at the moment, in my carbocation, the carbon with a positive charge. So I need to form that double bond with a curly arrow, but I also need to lose that hydrogen with the same curly arrow. So what I'm going to draw is a curly arrow that goes from the hydrogen to carbon bond into the middle of the bond that becomes the carbon-carbon double bond. So that should aim to go in the middle, not perfectly lined up on the screen, but it should aim to go in the middle, and that would be my final mark in this mechanism. Now, to finish this page, there is a different structure that we could draw, different carbocation, and so you can see here what's one of the options. But if I draw that intermediate again, I've got my positive charge, I've got my hydrogen. So that's what I've got in the question above, but I want to draw a different product. And what I'm expected to recognise is that this carbon down here also has some hydrogen atoms attached to it. And when they're attached to it, of course, I could lose that hydrogen in this final step of the mechanism. If I did, the product I would get would therefore put a double bond in a different position. So let me draw the final product. We'll get rid of that off of the screen. And with the product we're expecting would be a cyclohexene, but with the double bond on that vertical bond and that original hydrogen staying in place. So there would be my other option, using a hydrogen, I'll just label it up here, hydrogen from a different carbon, take that hydrogen away and put my double bond in a different position in the ring. Now this next question kind of introduces some chemistry that you don't always discuss, or certainly don't meet in A-level, rearrangements. And you can see carbocation D can undergo a type of reaction called rearrangement to form carbocation E. In this reaction, a hydrogen atom is bonded and its bonded pair of electrons move from carbon A to carbon B. And they show you the diagram. Now, this isn't chemistry you're expected to know. They've given you some information and you can interpret it. There you go. You're asked to use your knowledge of carbocations to explain why this rearrangement takes place. So let's look at the carbocations. If I focus first of all on carbocation D, there's the positive charge. Well, I know carbocation stability is linked to their structure. Are they primary, secondary, or tertiary? In this case, we have a secondary carbocation. There are two other carbon atoms bonded to the carbon with the positive charge. Whereas when I look at carbocation E and focus in again on that positively charged carbon, this time it's bonded to three carbons. I've got the carbons either side, here they are in purple, and the one at the top. That gives me a tertiary carbocation. And at this moment, I should be able to recall from my alkenes pack that tertiary carbocations are more stable. So I'm going to use that argument to focus in for my question here. So carbocation E is more stable. And so I'm saying here it's a tertiary carbocation, so it's going to have more alkyl groups and therefore a stronger positive inductive effect than that secondary carbocation. And one of the things that you'll see with my answer is I've been quite precise here. I've used the terms, let's go for the yellow pen, I think would be better. So I've identified as part of my written response that I know carbocation E is tertiary. I've also identified that the other carbocation is secondary, and I've linked stability to that positive inductive effect. The final question in this pack is a reaction of butan-2-ol. Concentrated sulfuric acid, and we're forming a mixture of 3 isomeric alkenes. 2 of these alkenes are stereoisomers. And perhaps the good thing to do here is to understand the question, is to draw out our butan-2-ol. I'll do it in the space that we've got just here. I've got 4 carbons. And an OH group on carbon number 2. Now, when I react an alcohol with concentrated sulfuric acid, I'm expected to recognise that that is dehydration, confirmed by the fact that I've got alkenes being produced. So I'm going to remove water from my alcohol. Now, that water has to be made using the OH group. It's the only oxygen atom in the structure. And going back through my notes, I know that I'm going to lose a hydrogen atom from an adjacent carbon. Now that actually gives me 2 choices. I could remove the hydrogen atom here from carbon number 1, and that would give me a double bond then between carbon 1 and carbon 2, and that's going to be my first product. That's going to be but-1-ene, and I'm asked to give the skeletal formula, so I've got to make sure I'm using the right formula, not just the structure of the product. I need to show it as a skeletal structure, and I need to give its IEPAC name, which is but-1-ene. Now that's one of the isomers done, but of course I could, instead of removing my hydrogen from carbon number 1, I could remove my hydrogen from carbon number 3. And so if I do that one in the blue pen there, What that would do is it would put my double bond between carbon 2 and carbon 3. Now, when I do that, I'm going to get my alkene that's going to give me stereoisomers. So when I draw that up, and you just have to bear with me as I reveal the two structures, there they are. These are the two alkenes that would happen when I get my double bond between carbon 2 and carbon 3. I'm asked to name both of these structures. Again, I've given skeletal formula. I'm going to call them butene because the double bond starts on carbon number 2 and it's a 4-carbon chain. So but for the 4-carbon chain and then 2ene. From there, obviously I need to recognise their stereoisomers. And so I should include that in their name. In this example I've got at the bottom, these two methyl groups are on the same side. It is the Z isomer. And of course in the top box, as you can see it on the screen, I've got the E isomer. And so what I would be expected to do in this section is include those features as part of the name. I would be expected to call this bottom one Z butene and this top one E butene. And I would not get the marks if I didn't specify the E or the Z. That was required in this question because I'm asked to name these compounds and the Z and the E is part of the name. That concludes going through these exam questions. So thank you for listening and paying attention. Hopefully Ree's been able to answer your questions if you joined us live in the room. If not, you've been able to watch some of the videos and you will be able to contact your teacher if you have any further queries.